Shielded high-voltage cable contains a conductive layer or shield that surrounds the insulated conductors. The shield serves several important functions. Firstly, it protects the conductors from external electromagnetic fields, often abbreviated as EMF, and electrical noise. Secondly, it reduces voltage stress on the insulation, improving its reliability and preventing premature failure. Shielded cable is particularly useful in areas with high EMF levels, such as near power lines or electronic equipment. Non-shielded cable, on the other hand, does not have a conductive shield. This makes it more susceptible to external EMF and electrical noise. It also results in higher voltage stress on the insulation, which can lead to premature failure. Non-shielded cable is best suited for areas with low EMF levels and where shielding is not necessary. Now let's discuss how corona affects non-shielded cable. Corona is a discharge of electricity that occurs when the voltage on a conductor exceeds a certain threshold. This discharge creates a visible glow, or corona, around the conductor. Corona can cause several problems, including power loss, electromagnetic interference, often abbreviated as EMI, insulation degradation, and conductor damage. Non-shielded cables are more susceptible to corona due to their lack of shielding. Corona in non-shielded cables can lead to several issues. Firstly, insulation damage, reducing its insulating capacity and increasing the risk of failure. Secondly, conductor damage, causing pitting or erosion over time. Thirdly, power loss due to energy dissipated in the corona discharge. Fourthly, EMI, interfering with nearby electronic devices. To minimize corona in non-shielded cables, it is important to maintain proper voltage and current levels, use appropriate cable sizes, and ensure proper installation and maintenance. When should you use shielded cable versus non-shielded cable? The choice between shielded and non-shielded cable depends on the specific application and environmental conditions. Use shielded cable in areas with high EMF levels, limited space, or where protection from noise or voltage stress is critical. Use non-shielded cable in areas with low EMF levels, larger spaces, or where shielding is not necessary. Here's a more detailed breakdown of factors to consider. For shielded cables, consider the following. Firstly, applications requiring minimal electromagnetic interference, such as sensitive electronic equipment or control systems. Secondly, environments with high levels of electrical noise from sources like motors, generators, or radio transmitters. Thirdly, situations where space is limited and cables need to be routed close to other equipment or structures. Fourthly, high voltage applications where voltage stress on the insulation needs to be minimized to prevent premature failure. Fifthly, installations near power lines, substations, or other sources of strong electromagnetic fields. For non-shielded cables, consider the following. Firstly, applications where electromagnetic interference is not a significant concern. Secondly, environments with low levels of electrical noise. Thirdly, installations where space is not a constraint and cables can be routed away from other equipment. Fourthly, low to medium voltage applications where voltage stress on the insulation is not a major factor. Fifthly, situations where cost is a primary consideration, as non-shielded cables are typically less expensive. The advantages of shielded cable include improved signal integrity, reduced electromagnetic interference, enhanced safety in high-voltage applications, and increased reliability in harsh environments. The disadvantages of shielded cable include higher cost, increased weight and size, and more complex installation procedures. The advantages of non-shielded cable include lower cost, lighter weight, easier installation, and greater flexibility. The disadvantages of non-shielded cable include susceptibility to electromagnetic interference, potential for signal degradation, and limited use in high-voltage applications. Now let's get into cable sizing. When selecting cable sizes for high-voltage applications, it is important to consider several factors to ensure safe and reliable operation. Firstly, current carrying capacity. The cable must be able to carry the maximum anticipated current without overheating. Refer to the National Electrical Code, often abbreviated NEC, Table 310.15b. 16. For allowable ampacities of conductors. Secondly, voltage drop. The voltage drop across the cable should be within acceptable limits to ensure proper equipment operation. Use appropriate voltage drop calculations based on cable length, current, and conductor resistance. Thirdly, insulation rating. The cable insulation must be rated for the maximum voltage it will be subjected to. Choose cables with insulation voltage ratings that exceed the maximum system voltage. Fourthly, environmental conditions. Consider the ambient temperature, moisture, and exposure to chemicals or other environmental factors. Select cables with appropriate temperature ratings and resistance to environmental degradation. Fifthly, installation method. The installation method can affect the cable's ampacity and voltage drop. Follow manufacturer's recommendations for cable spacing, support, and termination. In addition to these factors, it is also important to comply with all applicable codes and standards, such as the National Electrical Code, often abbreviated NEC, and local electrical codes. The National Electrical Code, often abbreviated NEC, provides detailed requirements for cable sizing, installation, and protection. It is essential to consult the latest edition of the National Electrical Code, often abbreviated NEC, and follow all applicable requirements. Proper grounding is also essential for high-voltage cable installations. Grounding helps to protect personnel and equipment from electrical shock and fault currents. Ensure that all cable shields, enclosures, and equipment are properly grounded in accordance with the National Electrical Code, often abbreviated NEC. For example, the National Electrical Code, often abbreviated NEC, Article 250 provides detailed requirements for grounding and bonding. The frequency of maintenance for high-voltage cables depends on several factors, including the cable type, application, environmental conditions, and operating voltage. However, some general guidelines include visual inspections, which should be performed regularly, at least annually, to check for signs of damage, such as cuts, abrasions, or discoloration. Thermographic surveys should be conducted periodically, typically every 1 to 3 years, to identify hotspots or areas of overheating. Insulation resistance testing should be performed every 3 to 5 years to assess the condition of the cable insulation. Partial discharge testing should be conducted on shielded cables every 5 to 10 years to detect signs of insulation degradation. Termination inspections should be performed regularly to check for loose connections, corrosion, or other signs of deterioration. In addition to these routine maintenance activities, it is also important to keep accurate records of all inspections, tests, and repairs. These records can help to identify trends, track performance, and plan for future maintenance. When performing maintenance on high-voltage cables, it is essential to follow all safety precautions and procedures. Firstly, to energize and lock out the circuit before working on any cables or equipment. Secondly, use appropriate personal protective equipment, such as gloves, safety glasses, and flame-resistant clothing. Thirdly, follow manufacturer's recommendations for cable handling, installation, and termination. Fourthly, use calibrated test equipment and follow proper testing procedures. Fifthly, never work alone and always have a qualified person present to provide assistance. Finally, ensure that all work is performed by qualified and trained personnel. Improper installation, maintenance, or repair of high-voltage cables can result in serious injury or death. Furthermore, environmental factors can significantly impact the performance and lifespan of high-voltage cables. Temperature, moisture, chemicals, and ultraviolet radiation can all contribute to cable degradation and failure. High temperatures can cause the cable insulation to soften and degrade, reducing its ability to withstand voltage stress. Moisture can penetrate the cable insulation, leading to corrosion and electrical breakdown. Chemicals, such as solvents, oils, and acids, can attack the cable insulation and conductors, causing them to deteriorate. Ultraviolet radiation from sunlight can cause the cable insulation to crack and become brittle. To mitigate the effects of environmental factors, it is important to select cables that are specifically designed for the intended environment. For example, cables used in high-temperature environments should have high-temperature insulation ratings. Cables used in wet or corrosive environments should have moisture and chemical-resistant jackets. Cables exposed to sunlight should have ultraviolet resistant jackets. In addition to selecting the appropriate cables, it is also important to take steps to protect the cables from environmental damage. For example, cables can be installed in conduits or cable trays to shield them from direct sunlight, moisture, and physical damage. Cables can be coated with protective compounds to resist chemical attack and ultraviolet radiation. Cables can be buried underground to protect them from extreme temperatures and environmental hazards. It is also important to perform regular inspections to identify and address any environmental damage before it leads to cable failure. These inspections should include checking for signs of cracking, discoloration, corrosion, and other forms of degradation. If any damage is found, it should be repaired promptly to prevent further deterioration. The choice of cable termination method is also critical for ensuring reliable performance of high-voltage cables. The termination method must provide a secure and reliable electrical connection, as well as adequate insulation and stress control. There are several different types of cable termination methods available, each with its own advantages and disadvantages. Some of the most common methods include heat shrink terminations, cold shrink terminations, and epoxy terminations. Heat shrink terminations use heat to shrink a plastic sleeve onto the cable, providing insulation and stress control. Cold shrink terminations use a pre-expanded rubber sleeve that shrinks onto the cable when a core is removed. Epoxy terminations use epoxy resin to encapsulate the cable, providing insulation and mechanical support. The choice of termination method depends on several factors, including the cable type, voltage level, environmental conditions, and installation requirements. It is important to select a termination method that is compatible with the cable and meets all applicable codes and standards. Proper installation of cable terminations is essential for ensuring reliable performance. The termination must be installed in accordance with the manufacturer's instructions and all applicable codes and standards. The cable must be properly prepared, including stripping the insulation and cleaning the conductors. The termination must be properly sized for the cable and voltage level. The termination must be securely attached to the cable and properly insulated. The termination must be protected from environmental damage such as moisture and corrosion. Regular inspections of cable terminations are important for identifying and addressing any potential problems. These inspections should include checking for loose connections, corrosion, cracking, and other signs of deterioration. If any problems are found, they should be repaired promptly to prevent cable failure. Remember to consult with qualified electrical engineers and follow all applicable codes and standards when designing, installing, and maintaining high-voltage cable systems.